In today's video, we will be talking about the mirror equation for concave mirrors. And after watching this video, you should be able to tell me what kind of image will be created from a concave mirror, and be able to use the two equations dealing with concave mirrors. So let's get right into it. Just a refresher, the couple lessons back, we were talking about ray diagrams, whether it was with plane mirrors or concave mirrors, and those diagrams are great, but the problem with those types of diagrams is they don't provide any numerical information in terms of how far away is the image formed from the mirror, is it magnified, and if it is magnified, by how much. Those are all questions that the ray diagrams don't really answer, and so we're left with, well, like, what do we do? Well, the answer is we can start to use these equations, all right? And there's the first equation I want to talk about is what I'm just calling the mirror equation. And basically, the mirror equation expresses a quantitative relationship between the object distance, which we're going to use as the symbol of DO, object distance, and then the image distance, which is DI, and the focal length, which we've been talking about as F. Okay, and this is basically how the equation is set up. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. Okay, so that is the mirror equation, and we'll be using this quite a bit for concave mirrors, and then we're going to talk about it again in a different type of mirror later on down the road. All right. The second equation that we'd like to discuss is the magnification equation. And basically, the magnification equation relates the ratio of the image distance and the object distance to the image height and the object height. Okay, so the actual object height, how does it relate to the image that's being produced by the mirror, the size of that image that's being produced? And that equation can be written as this: the magnification, which typically is just a numerical value, and if it's above 1, it's being multiplied by that. So if you get a magnification of, say, like 2, for instance, it's going to be 2 times the object size. And basically it equals the height of the image, or also known as high, over HO, which is the height of the object. And that is equal also to the negative distance of the image over the object distance. Okay. And again, this equation, it looks maybe a little complex at first, but once you start to use it, it's not that bad. And so I'll do a few example problems later on in this video using these equations, and that might help clarify some things if you're a little bit confused. But just keep these two equations in mind as we continue on. Okay. Signs are actually pretty dang important in these equations, and it's important in the mirror equation, and it's important in the magnification equation. And I know there's a lot on this slide to write down, so I'm just going to go through each of these bullet points real quickly to discuss what all these signs mean. If you have a positive focal length, the mirror is going to be what's called a concave mirror, which is what we've been talking about recently, these concave mirrors. If the focal length is negative, the mirror is called a convex mirror, which we haven't talked about yet, but we will later on. Okay, so if you have a negative focal length, you have a convex mirror. If the image distance is positive, the image is a real image and located on the same side as the object of the mirror. Okay, so basically, if DI is positive, it means you have a real image. Right? If you have the opposite, which would be negative, DI is negative, it's called a virtual image, which basically means that the image is being produced on the other side of the mirror, basically where the light isn't going. You have a virtual image produced. The HI, if that is positive, if the height of the image is positive, it is upright. Okay, so it means that it wouldn't be like flipped, and it is also virtual. Okay. If the HI is negative, the image is inverted and real. So again, it's a lot of stuff, and we're going to make a chart in class to kind of help remember this. But these are the sign conventions, and so if the answer is positive or negative, it's actually very important because it's going to tell you a few things about the image that's being produced. Okay, let's go right into an example problem, and let me just change my colors here so that we can actually do this problem. It says a candle is placed 0.24 meters in front of a concave mirror that has a focal length of 0.12 meters. How far from the mirror is the image of the candle located? Okay, well, as always, I highly recommend drawing out your problems. Okay, so I'm going to draw a principal axis, right, and then I'm going to draw my concave mirror, and here is my focal length, which they say the focal length is 0.12 meters. Okay, so from here to there is 0.12 meters. And then I have a candle, which I will just represent with an arrow. You don't actually need to draw a real candle. And that candle is, it says 0.24 meters from the mirror. Okay. So how far from the mirror is the image of the candle located? Okay, so now we're wondering, this candle, it's producing an image on this concave mirror. How far away is the image from the mirror? Okay, so I'm going to use the mirror equation, which basically says 1 over f equals 1 over do plus 1 over di. Okay, and that's what I'm trying to find out, is di, the distance of the image. Okay, so if I just plug in my numbers, I get 1 over 0.12. Okay, that's just 1 over the focal length. And then I'm going to bring this do over to this side. Okay, so I'm going to subtract 1 do from the right, and we do the same to the left. So now it's minus whatever 1 do is, and that is going to be 1 over 0.24 meters. So 1 over 0.24 meters equals my di, 1 over di. Okay? And basically, if you do that math, you get an answer of 0.24 meters. All right, and that would be my answer. So the image distance is 0.24 meters. All right, let's do another example problem. A 4 centimeter tall light bulb is placed a distance of 45.7 centimeters from a concave mirror having a focal length of 15.2 centimeters. Determine the image distance and the image size. Okay, as always, I recommend drawing a picture. And I'm going to draw this picture kind of smaller because I got a lot of things going on in this problem. Okay, so here is the focal length. And the focal length is 15.2 centimeters. And it's a light bulb, right? Yep. My light bulb, which I'm still going to draw as an arrow. No change there. My light bulb is 45.7 centimeters. All right. So knowing, and this light bulb is 4 centimeters tall. Okay, so the first thing I'm going to do is I'm going to find out the distance, okay, the image distance. And so I'll be using the mirror equation, 1 over f equals 1 over do plus 1 over di. All right, and I know the focal length is 15.2 centimeters. Okay, right there. And I know that the distance of the object is 45.7 centimeters. So I'm going to try to get this term by itself. Okay, and I'm going to bring 1 over do to the left-hand side of this equation. And if I plug my numbers in, I'm going to get 1 over the focal length, which is 15.2 centimeters, minus 1 over do, which is, let's see here, 45.7 centimeters, equals 1 over di. And basically, if you do the math and you solve for this problem, I get a di of, or a distance for the image of 22.8 centimeters. All right, so that's nice. So that does this part, determine the image distance. Okay, we got that. All right, now I want to know how much is this image magnified? What is the image size? Okay, so we're going to be using the magnification equation. So the magnification equals hi, the height of the image, over ho, the height of the object, equal to negative di over do. Okay, and we don't really care about the magnification per se. I mean, we could certainly figure that out if we want to, but what I'm really concerned with is this basically a ratio right here. Okay, and that's why I figured out di first, because once I figured out di, I then knew di, do, and ho, and I can then figure out hi by basically cross multiplying and then dividing. So this will make more sense once I maybe plug some numbers in. The height of the image, I do not know. So that's what I'm trying to find out. And the height of the object is 4 centimeters. And I have a di of 22.8 centimeters. And a do of 45.7 centimeters. And if we do that math, I get an image height of 2 centimeters, right around 2 centimeters. And this would be negative, indicating that it would be inverted, okay, or upside down. All right. So that's just 2 example problems. There's obviously many more we can do, but we can do those in class. That takes care of this video. I will see you guys next time.